Oh, yeah. Now I'm here. I still think when I was learning oh no, I got way triangles and I've gotten way better at mathematics since college than I did in high school. I don't know why. I think it's just forced me to get better. I definitely like the yeah. So it's like, oh, this is how they came up with it.
Well, I think we could get started. Welcome back, everyone. So we're about to conclude week 13, which means we're moving into an examination week coming up. As far as exam 3 goes, it's exclusively going to be these sections. You're going to have some problems that involve with dealing with the limit of a sequence, but we didn't spend too much time in that particular section, so not a whole lot of problems there. After that, section 11.2 includes the integral test and a p-series test. It doesn't hurt to actually write these out. Let's write these out as we go. So just for a breakdown of what's going on in our third exam, section 11.1, this one's going to involve testing a sequence for convergence divergence, but that just means you're taking a limit, seeing if it comes out as a finite number, or if it doesn't exist or comes out as infinity. Then for the next section, 11.2, 11.2 has the integral test. I mentioned a lot about the integral test, about how it's not the necessarily optimal test in every situation, but when it works well, it's an incredible test to have in our toolkit. But the thing that's gone wrong with the integral test over the years is there's been some exams where people attempted the integral test on almost all the series problems and series problems rather. That turns it into a really brutal and long exam. And so I'm going to give a hint on the integral test just so that we're not in that same situation. The exam that deserves a name. The exam will say to use this test. So that'll just be baked in the problem. The problem will say use the integral test to show if the series converges or diverges. That takes a load off of worrying about how all the other tests fit in. But this is where all the other tests are going to fit in next. This is part of the exam where we have other series we have to look into. On 11.2, one of them is going to be a p-series. But we have to identify that it really is a p-series on the exam. So expect one of those. There's also going to be a problem. Let's see, I think I'm pointing to the wrong sections here. That's not the biggest problem, but let's fix that just so we're not overly confusing ourselves as we're trying to do an exam. Integral test is 11.3. Sorry for that omission. It's been a while, I guess, since we ran through those section titles. And the p-series test is also in section 11.3. So 11.2 contains the geoseries test. Is probably the one I was thinking about. Geoseries is going to be there, as well as test for divergence. I'm going to include exactly one problem where test for divergence is the natural fit. So expect that one to fit in just nicely on one problem. Your conclusion is therefore diverges. You should expect a geometric series as well. But I'm not too worried about finding the exact sum. You're just going to use the formula to determine if the ratio is less than 1, converges, greater than or equal to 1, diverges. But all these things in blue, these are the ones that we have to spot to determine if we should use the geoseries test, if we should use test for divergence, and so on. Then 11.4, this one contains comparison tests. And that means there's some creativity here. I'm going to have a problem that does include a comparison test. And you might use the direct comparison test where you have to use a less than or greater than estimation, or you might be able to fit the limit comparison test on that one. So there'll be some freedom for how you analyze that test in that section. Coming up after that, 11.5. Let's see, 11.5 had alternating series. So there will be a alternating series problem. The dead giveaway is the -1 to some power of n, maybe power n minus 1, something like that. Let me get that comma out of there though. Alternating series this way. Also in section 11.5, we had some things about absolute convergence, conditional convergence versus divergence, but I'm not going to go in too far into that kind of dichotomy. We're just going to be doing ordinary convergence or divergence in that section. And so let's see, I think that finishes up the test that's in that section. And the next one, 11.6, this is where we started getting into the bigger test for absolute convergence, the ratio test, as well as the, let's see here, the root test is what it was called. I'll have a problem that fits well for root test and fits well for a ratio test as well. Then finally in section 11.8, let me change that color again. Section 11.8, we'll have a power series now. We'll have a case where R equals 0 or infinity. So that's going to be the really fast one where you pretty much just use ratio test and then you're done. And there will be a second one where the case is, say, R equals, it could be any kind of value, but let's just say 4 as an example. So not exactly 4 on the exam, but a case 4, which means we have to do further testing on the boundary. So that's pretty much going to be the whole exam. So I'm looking into a problem on a sequence. There's going to be a geoseries, a test for divergence, p-series comparison test, alternating series test, and a ratio test. But it's not going to be like a p-series problem comes up with 3 parts. It's just going to be one series. So not as long as exam as it seems. Exactly one integral test, the instructions will say what to do. Essentially anything in green, the instructions will be very descriptive of what methods you should be using. If it's a power series, you're absolutely just using ratio test. That's our only tool. So the harder part of the exam is really looking into the things in blue to determine which one was the p-series, which one was the geoseries, which one fits test of divergence, which one's the alternating series test, and then that gets you towards the rest of the exam. Well, any questions at the moment, folks, with the exam content? Just so I don't lose this page, let me screenshot it right here. And if you want to come back to those notes, you can come to the YouTube video, which is tedious to find sometimes. I'm also going to put it under our exam 3 information. Let's just call this in class exam 3 discussion. And here's our first screenshot on that. Okay, so this is what the exam consists of. And as you study the exam, probably you've been using this document already. This is the provide formula sheet that we mentioned. It has all the tests that we're going to be looking into, as well as information for section 11.8 specifically on dealing with these kind of power series here, where we mentioned there's going to be one problem either of these 2 cases and one problem with this kind of case here. Then the rest of the information for all the other tests is provided on that document. Next thing you'd want to take a look into when you're studying for this exam is definitely the homework problems. In fact, the homework problems are designed to be as similar as possible to the lecture notes. And the lecture notes were also designed to be similar to the homework problems because all this stuff is going to be highly similar to the 3rd exam. The best versions to see the most similar questions on the 3rd exam is a tie between version 1 and version 2. Version 2 might be a little bit better because these are actually the exact homework problems that you've been solving. And so you've been working on these before. You might get some extra kind of studying, seeing them a second time. So if you're behind on any one of these sections, the most valuable thing you can do to study to get a great grade on exam 3 is get caught up on these. On Friday, I'm going to start converting over to grading papers. It might continue into Sunday, but my main objective of grading is to get all of these returned. Even if you turn in hard copies, I'll have them scanned and I'll send them to your IUCU email address so you can get your feedback ahead of that exam. Well, any last questions, folks, about the exam so far? Or any questions that folks would like to take another look into? Any review problems that seem helpful or anything along those lines? Okay, well, what we'll do next is go back to section 11.10, the part 1 section. But if any time we're working through those problems, if a question does come up, don't hesitate to interject. I'll be happy to pause wherever we're at in section 11.10 and take a look into that question. But this is where we left off before. We were doing a power series, oh, where'd it go? Power series representation. Okay, it's over there somewhere. There we go. We did a power series representation of cosine. And it's a pretty tricky problem. Take a look into example 1, part B as well, where we had to maneuver through the re-indexing phase of all this. Anytime we have a list of zeros coming in play, this kind of strategy has to be used. This happens in the homework exercise as well. But I don't think I'm going to do this on a final exam. This requires just a little bit of extra patience and probably throwing away scratch paper, that kind of stuff, trying a couple times. Not a great exam question. But for the homework, we'll have the time and mental space to run through this kind of operation. We decided after putting this all together that the power series representation of cosine x was take the expression for the nth order derivative of pi, it's either positive or a negative one. That means when we go to write the coefficients, we're just dividing by 2n factorial, and we put in that alternating part. Bringing it back over here, though, is a little bit tricky. If we're dealing with evens, then sure, we re-index and we start at 0, and that's just how the re-indexing is going. But you have to have 2n here, and you have to have 2n here. That's kind of easy to miss. This n and this n stay the same. So this gives you all the evens. And in a certain sense, that should make sense, right? Because this term that involved the 0 would have been a coefficient in front, 0, and then x minus pi to power 1 on this one. The very next one is the even, the next one is odd. And so if we put in this, we're not capturing it. We're putting in even and odd powers, but all of the powers here should have been, sorry, wrong line, should have been even altogether. So even right there on the power for x minus pi, we have to have the 2n. Last tricky bit, this is new to Taylor's series, is we have to rewrite the center or re-express the center. We did that in all these computations. And then down here, we had to go x minus pi. For Maclaurin series, it would have been just x power 2n. So that's our cosine as a Taylor series centered at pi. This would give you a great approximation for any computations nearby pi, like say cosine 3 or cosine 3.5, something like that. Next thing we have to do, though, is validate our radius is really infinity on this one. So let's take those steps next. To get a radius at infinity, we take the limit as n goes off to infinity of an plus 1. Let's maybe write that in first, since it looks like it's going to be involved. An plus 1 is going to be equal to negative 1 power n plus 1 over 2n plus 1. Well, 2 times the group x plus n plus 1 is better said, factorial. I'll place the x minus pi into the numerator. It's now to power 2 n plus 1. So fixing these exponents, we have negative 1 to the power of n plus 2. That's an odd expression we mentioned. That simplifies to just negative 1 power n, but we're going to take absolute value on that. So no harm done just leaving it exactly the way it is. Next, we can factor out x minus pi. Let's see, or let's just rewrite this, x minus pi 2n plus 2. And down below, it's 2n plus 2 factorial. Now we just take this whole thing, bring it down below right here, but let's do the factoring in this spot. -1 power n plus 2. We're going to leave behind power 2 on x minus pi, because we're going to cancel with power 2n, eliminating everything else. So x minus pi power 2 times x minus pi power 2n. Then on the factoring for this one, we're going to cancel 2n factorial into that. So we should rewrite 2n plus 2. Factor even further, 2n plus 1. And then at the 2n, we're done factoring. Just tie it off with the factorial. And it's the same exact expression as up here. Okay, once we have all that, multiply by the reciprocal of all of this stuff right here. That will put 2n factorial up into the numerator. -1 power n plus 1, x minus pi power 2n down in the denominator. And finally, our ratio test is ready to run. Forgot to name it, but let's do it here. Cancellations for this is going to be the x minus pi power 2n. Looks like just anything with the 2n is going to cancel off. 2n factorial. This is canceling due to absolute value, the -1 to a power. So all that's left behind, x minus pi squared, and that denominator. You know, if you did your limits right here, that would be okay, because we are looking, oh, hang on. Not too sure what I did there. There we go. If we do the limits right here, it's appropriate, because we are looking at a constant being divided by something that grows larger and larger without bound. That's not a bad thing to say just right at this step. We've run the ratio test so many times that that's a good shorthand. I would say on this one, automatically 0. Does that make sense to folks at the moment with that limit? Okay, we get 0. This is less than 1. We're mentioning that because that now implies convergence. And this happens for all x. So r is infinity as expected. Really, you may not have had to write that stuff because we set it right here as well, r is infinity. All the limit coming out of 0 did for us is it just validated that our suspicion is right. This has convergence, absolute convergence, for all real numbers is what this is expressing. So that's a pretty powerful tool. We'll see in the very next section what weird problems you can integrate now that this is finally on the table. Any last questions, folks, on surviving this cosine expression? Okay, I find that this one is often sometimes one of the bigger head scratchers in this section, 11.10, the first part, because reindexing is just weird. So if you have questions about that when we're in, say, a closed week coming up, starting on the 28th, all we're doing on the 28th is finishing whatever last section that we started, potentially on the 24th. We're not going to introduce any new content. Then from then on, we're just going to be reviewing for the rest of this week here. If you want to see more of these, how they would go for extra practice, don't hesitate to ask. I'll be bringing in review problems for that review week as well, but you're also welcome to bring in whichever question you would like to discuss. So far, for the sake of getting through the homework, here is our, excuse me, not getting through the homework. For getting through the notes right here, here's the last problem that we want to get through. This one's not challenging in the same way that the cosine problem. That last problem was challenging just because of the reindexing. This one doesn't need reindexing. It's just a really hard pattern to spot. So let's work through this one really carefully and do the careful work of finding the right pattern recognition for that numerator, the nth order derivative at the center. This time the center is 4, implying already this has to be a Taylor series. But either way, we start off by writing f of x is natural log x. Then f at the center will just be f at 4. And that gives us natural log 4. So we're off to a great start. For the next rows, we differentiate and then evaluate. And we know for sure f prime of x is 1 over x. And I would absolutely write in f prime of x is 1 over x in almost every situation. But this is a case where you do algebra and calculus a little bit differently. It's a good idea to call this one x power -1, just for ease of differentiation for all the next derivatives we're going to be taking. So there's our 1 over x. Evaluated at 4, we get 4 power -1. Big shift from the first term and the very next term. So that's a little bit concerning, but we'll do just our best we can. Now take it to the second derivative. Following the pattern, now we're just using the power rule. We'll get negative x power -2 on this one. And over here on this row, I forgot to put in f prime. Not a super big error, but it's confusing. We should keep the primes lined up, or else that could actually affect our pattern recognition on the last steps. Last steps of step 1. This is a big process. So second derivative at 4 means take negative 4 power -2. So something new came in, but we are seeing a bit of a pattern. First order derivative involves -1 power. Second order derivative involves a -2 power, so that's kind of nice. But it went positive negative, so we have an odd term that doesn't fit, alternating, but the 4 power -1 power -2 seems to be the firmest thing nailed down. Let's keep on going. Third order derivative at x becomes, now it's a +2, x power -3. So something new has come up. We have that the third order derivative at 4 is 2 times 4 power -3. So analyzing the power, or analyzing the pattern on these negative powers, they're doing something that's reasonable to track. Every higher order derivative gets 4 to a power negative the order of the derivative. But we have a non-standard term, we have alternating, and this is new. We have coefficients showing up as well. And let's see how this 2 could fit in. Absolutely, there's a factorial pattern that's coming in. Let's do maybe 1 or 2 more to see if we can really spot and nail down that pattern. But that's what's going on. It's alternating, involves negative powers of 4, a non-standard term, and factorial all in one. Just from an ordinary logarithm, kind of oppressive for that. So take the fourth derivative. Now it really looks like factorial is coming up, right? We get -2 times 3, x power -4. The fourth order derivative at 4 is then -2 times 3 times 4 power -4. That's definitely a factorial showing up, but let's do it once more just to get extra data. It's all about pattern recognition. The more data you have, the more striking the pattern becomes. So fifth order derivative at x. This one is going to be, now back to positive, 2 times 3 times 4, x power -4. That's a definite factorial we're looking into. This is a good spot to pause, though. Some people might have multiplied this to get a -6, then multiplied this to get a +24. I would say that's a bad call, because if you multiply these together, we're hiding the factorials. And even worse, definitely don't multiply this stuff out whatsoever. That's not going to help us to express these as integer digits, or excuse me, as rational numbers. 0.25 here doesn't help us, for example. Seeing them explained in this way is what helps. And it's weird because we're resisting our urge to simplify things. That's our algebraic training. But for pattern recognition, we need it complicated, not simplified. So fifth order derivative at 4 is 2 times 3 times 4 and times 4 power -5. From all of that, we should be able to get this. Let's say here. Therefore, the nth order derivative at 4 will be equal to something. If you're writing down the pattern right now, I'd say that would be a good idea. If you want more inspiration, if you're not too sure what to write down here, That's okay. Do further work on this column. This column can now be re-expressed as, let's say, this is altogether 4 factorial, 4 power negative 5. This one is negative 3 factorial, 4 power negative 5, positive 2 factorial times 4 power negative 3, then negative 1 factorial times 4 power negative 2. Finally, 0 factorial fits in there. That's always weird. I feel like we always have to make a comment. Don't forget 0 factorial is a 1. So there really is a 1 times 4 inverse right there. That allows us to write 0 factorial power negative 1. And I have nothing on this one. There's nothing I can do to make a natural log 4 fit that kind of pattern. This is something new that happens in this problem. Right at index 0, this completely defeats the pattern. So this is a pattern break at index n0. Now, all of their indices, n is 1, 2, 3, 4, 5, and so on, up to the index n, we have a strong pattern that we're looking into. Let me fix my spelling here. If the pattern ever breaks, usually it's going to be on the first term for this kind of context. You have to write an expression that what we're about to say here for the nth order derivative is only going to be valid for n greater than or equal to 1. It's a good thing to write in because it's going to remind us you have to come back to that term. That is the very first term of the power series. It's going to lie outside of the summation because if it doesn't fit the pattern, it's not going to go inside the summation whatsoever. So finally, putting that all together, the nth order derivative at 4, let's take a look. We're going to start our indexing at 1 on this. And one fact about it is that it's an alternating pattern. So we might go in with a negative 1 power n, and then just take a look. If you plug in 1, you get a negative sign, but we have a positive sign, so we just bump the power up or drop it by 1. Plus 1 or minus 1 is going to give you the same series. I usually go the route of increasing the pattern, but that's just my habit on this one. So we've got the alternating part down. So aside from the fact that it alternates, there's also a factorial. But check out how it relates. 0 factorial to the first derivative, second derivative to factorial 1. The factorial is always 1 less than the order of the derivative we take. So we have to go n minus 1 factorial on this thing to get the right factorial to come into play. The final thing is that, well, there's a 4 to the order of the derivative. That one wasn't too hard to spot. Go 4 power negative n, because just like we have the 5th order derivative, we got 4 power negative 5. So this is the pattern for the derivative evaluations at the center. We get this expression, but it's only valid on indexes greater than or equal to 1. Any questions at all, folks, getting that pattern set down? This is a pretty rough problem also, I want to say. This one would be just being kind of rude, I'd say, on a final exam for a question. If this was a real final exam question, I'd probably grade it with the understanding. I just want to know how much you know about this whole process. If you got stuck here and this was a real final exam question, it probably gets a lot of partial credit because I'm looking into how you approach a challenging problem like this one. But I don't get into the habit of writing out extra challenging questions, stressing out everybody on final exams. So this one is more something that can happen in a homework question, is what it's meant to directly support. This is a valid thing that you have to worry about in homework problems. But also look how far we've come. If you go to section 11.1, just about every class, ours included, we didn't like this problem. It's uncomfortable in a way. Find a pattern for the generic nth term. We did that here carefully, and this one wasn't too easy to do on. But you know, the purpose of all that was this. We found the pattern of the generic nth term, but we had to do a lot of practice to get to that point. That's why we've been doing these sort of problems on essentially every single section starting in 11.1. It's because it's culminating in this kind of work. But if we can get here, our job is nearly done because all we have to do is say, what is the coefficients, Cn? We have the numerator, we just need the denominator. So we can rewrite this by saying Cn is nth order derivative at the center 4, divide by n factorial. So these are the coefficients. Don't forget, they only work for n greater than or equal to 1. Let's put in the numerator, negative 1 power n plus 1, n minus 1 factorial. And we can move that 4 power negative n if we're annoyed by it. This is totally up to you. I'm going to drop it down into the denominator for a positive power, and then copy in n factorial. Whenever we have dual factorials, though, it's a really good idea to simplify this down. It isn't a requirement, but it's going to make everything easier, especially the step of finding its radius of convergence. Let's do a little bit more work on this one. We have negative 1 power n plus 1, and we wouldn't factor this one down. We factor the larger one, the one with the larger base factorial. So let's look to the denominator. 4 power of n times n minus 1 factorial. We can tie a factoring there, because that's now going to cancel with the n minus 1 factorial. Really same kind of steps we always take in the ratio test. Maneuver your factorials for huge amount of cancellations, and that's what's happening right there. So our Cn coefficient is not as complicated as it really looked like. All that survives is negative 1 power of n plus 1, n times 4 power of n. So put that all together, and we can say, let's come back over here. Not too sure why I keep hitting that. I think one of these keys is getting like jammed up with chalk and it's getting stuck. Probably, definitely. But anyways, other than the keyboard going out, we're grabbing the function natural log x that we started with. I'm going to use this to zoom in and out so we don't get random beeps. So natural log x is now going to be equal to a power series, but this term is still the one term that was off. We cannot incorporate it inside the summation. So we begin by putting in natural log x is natural log 4 plus the pattern broke at index n is 0. So in our power series summation, our index starts really at 1, not at the 0 we might be expecting. So now we do a summation from 1 to infinity of whatever the Cn coefficient is. Here it is in its simplified form. Negative 1 power n plus 1, n times 4 power of n. And then we go x minus the center, power n. Let's double check. Center was given as 4. So 4 would go here as well. That deserves some highlighting just to tie together the role in the center and building the series. So there's our series. And on this one, it's kind of hard to tell what the radius of convergence would be. Except if you think about this, we're doing a power series centered at x minus 4 for a natural logarithm. And the logarithm does not have a domain that's infinite in length. So if we center this off at x minus 4, we have a distance of 4 to go from the center on x until we hit a discontinuity. Let's just throw this graph up just to really highlight what we're saying here. So here's the natural logarithm of x. Our center is right here at 4. That means x moves around the center. It can move to the right, seemingly pretty far, except not quite so. The distance I can go to the left is 4. It's actually less than 4. You'll hit a discontinuity if you go exactly a distance 4. So if you looked into that, you have some interesting information on the table. My claim is radius of convergence has to be 4. This is not even a coincidence. There's real theorems that supports that. But we need to be sure, right? Let's hit this with the ratio test and see if we really get radius 4 on this one. Any questions, though, looking into that kind of view of this? Wow, I'm not sure what that was. This computer probably deserves a restart. That's the buttons I hit whenever I'm going to do a screenshot. Okay, it worked that time. Who knows what's going on with this keyboard? But we have a radius 4. I'll put the screenshot down below just as a reminder. Sometimes you can kind of reason through this. If you have any kind of situation that comes up like this, in some other context, for example, you can double check your work on the ratio test to see did your expectations come out the way we might have thought it they would. So this is going to be our official answer. I want to also say right here, indexing at 1 in this color, just to convey that weird trickiness. Now we're double checking what we were saying right here. Writing down a diagram is not a mathematical proof. It's easy to kind of convince yourself of something that's not true. So we're looking into this closely now. Take the ratio test, take the ratio, yes, test, and then take an plus 1. An plus 1 is negative 1 power n plus 2. And then we'll get x minus 4 power n plus 1. Denominator will contain n plus 1, 4 to the power of n plus 1. Now we're ready for the limit. Take the limit, n goes to infinity. In absolute value now, negative 1 power n plus 2. X minus 4, I'll factor out 1 power. I'll leave behind x minus 4 power n. Down below, it's n plus 1. I'll factor out 1 copy of 4 and leave behind 4 power n. Then we multiply all this by the reciprocal of the nth term from up here. So we take the reciprocal of this. N times 4 power of n forms the numerator. The alternating part, negative 1 power n plus 1, as well as x minus 4 power n go down below. Now, the fun part is the cancellation. We get anything to power n is automatically gone. Negative signs are gone. And this is what we get. This limit doesn't just go to 0 in a nice way and wipe out and conclude immediately. This is one where we might want to take a little extra time on it. I want to factor out the constant. The limit operator is on an index n, so we can take out x minus 4 as a constant, as well as that 4 in the denominator. It'll leave behind the limit as n goes to infinity of what's left. Looks like an n right here. And denominator is n plus 1. Notice this time the limit is not 0. Anyone see the value of this limit here? Well, both answers kind of right. If you incorporate the 4, definitely a 1 over 4. If you're looking into just a limit, it would be a limit of 1. Good call, folks. Carter says, how does the negative 1 n plus 2 cancel out with the negative 1 n plus 1? Well, that's a really great question, Carter. It really doesn't cancel out with it at all. But what's happening with those negative 1s to a power is, let's take just one additional step here to clarify with it. So before getting to that line, you could take an intermediate step that would look like this. X minus 4 would have absolute value attached to it. So I'm going to take it out like we did on the last step. Absolute value of 4 is still just a 4, so that would stay inside. And here's that middle step that step in the middle. Take the limit as n goes to infinity. And there is a form of cancellation going on with this. But you could also just rewrite this absolute value operator attached to the x minus 4. When you're multiplying things together, you can separate out your absolute values. Take the absolute value of negative 1, n plus 2. We took the absolute value of x minus 4 and we just dropped it right inside over there. Absolute value of n makes no effect. Absolute value of n is n, since n is a positive quantity. Down below here, same idea. This is still just an n plus 1. absolute value of 4, we already chunked over there, it's still just a 4. But then we have to take the absolute value of -1 and +1. So the formula that I'm kind of writing or implying here that I didn't quite write in is that the absolute value of A over B is the absolute value of A divided by the absolute value of B, that's a B right there, as well as the absolute value of A times B is the absolute value of A times the absolute value of B. You have to be super careful with these formulas because the absolute value of A plus B is absolutely not the absolute value of A plus the absolute value of B. Whether you went plus or minus, this is a broken equation. Just like, say, taking the square root of A plus B. We can't factor that up. Same with logarithms. Addition has messed up the algebra here. But if things are just being multiplied and divided, absolute value is going to attach to every single factor. The moment you have something like that, it messes it up completely. So it's kind of nice. Everything that we've been writing out with the ratio test gave us numerators and denominators with multiplications going through, like both versions of those formulas to work. And now the real cancellation is right here and right there. They just wipe out their absolute values. They could cancel inside right over here, but it would still leave a -1, let's see, to a power, not necessarily involving n. But then absolute value is just going to kill the -1 regardless again. But does that make sense on looking into the absolute values a little bit closer on those parts? Yep, absolutely. Other questions with the limit so far? Okay, well, with what we've got, that limit is a 1. So this turns into, it just looks funny. Let's see if we can kind of make that look about the size I'd write it. This is going to turn into absolute value of x minus 4 divided by 4 times 1. And now we do something that's always interesting on the ratio test. We go less than 1 because that's the condition on which the value of x would converge for the power series. But then this implies absolute value of x minus 4 is less than 4 once we multiply both sides by 4. And if you get to here, this fully shows us that the radius of convergence is exactly 4 itself. Although that is taking kind of a shortcut. You could also say -4 less than x minus 4 less than 4, add 4 to both sides. 0 is less than x, less than 8. So the diameter of this interval would be 8, but take its length, divide by 2. The radius of the interval is 4, is now what this is saying. That matches up with our expectations from right up here. Here's our power series. It's a strange one with terms that are off indexing that's non-standard. And it's a Taylor series as well. So that's why it has a center and a finite radius of convergence. This problem didn't ask us to test the interval. So notice it said way up here, find the radius of convergence. It did not say find the interval of convergence. So that's why we can stop right at this step the moment we do get the radius. In section 11.8, the reason to mention that is because in section 11.8, this is the last section relative to exam 3. And in that section, we ran a lot of ratio tests. Let's take a look at a particular one. So here's a ratio test, same as the kind of one that we're dealing with. It had a finite radius on this one. We ran the test, found out the radius is 3, but we couldn't stop here. And this is the same kind of situation on the exam. We can only stop if the radius is 0, implies the interval is 0. If the radius is infinity, implies the interval is infinity. But if it says find the radius and the interval of convergence, we had to go further. We had to actually test at -3 by plugging -3 into the original series up here, getting an expression out. But this is not too dissimilar from the exam. The further testing is going to be pretty fast. It might be a p-series. It could just be something like this. You name it as harmonic, alternating harmonic, and the foregone conclusions about them. So that's what's going on so far with this kind of problem. But looks like we conclude the notes, folks. That one was our last one for the set. Any last questions whatsoever with finalizing this one? Okay, let's save this up. And we are done with the hard part of section 11.10, Taylor series, Maclaurin series. The next section is mostly smooth sailing, but we're going to look into one kind of interesting topic, the binomial series. The reason we're looking into the binomial series is Calculus 2 has a really great opportunity. When we look into these formulas, we constantly say there is a huge breakdown with a plus. You can't break down absolute values in this way. You can't take a plus b to power 2 and say that it's a squared plus b squared. It's really a squared plus 2ab plus b squared. Anything that involves addition just breaks down our patterns. Our normal pattern is a times b squared is a squared b squared. But put in a plus and everything gets really complicated. It's almost just not fair, right? There's got to be a nice way to do even at least this on some problems. So what about the square root? Square root of a plus b is absolutely not equal to the square root of a plus the square root of b, but there is a way to do something like what we did right up here. Even though it's not equal to that, just like a plus b squared is not a squared plus b squared, there is a formula. It's worse than this one, but we can derive that formula. And if you ever have to distribute a root through terms like this, we can do it, but we'll see what it looks like to decide if we want to do it as well. So that's the binomial series. Let me just make sure I save these notes. And that's what's going on in the first part of the second document. After we get through the binomial series, what we're going to do next is put all of our Taylor Maclaurin series together. Maclaurin series actually started in section 11.9 itself when we started working with the geometric series. So this was our first power series, or excuse me, Maclaurin series, better said. Radius was not impressive, just a 1. But then we got some interesting results. We showed that this one takes on that form with radius convergence. I believe you'll do this one in the homework. We showed this one for cosine. And some of these were done by the author himself in the reading. Tangent inverse takes on an interesting route. Natural log 1 plus x, kind of similar to what we were doing, has this format. And here comes the binomial series. If you have 1 plus x to power k, you can use a so-called binomial coefficient and write out the power series for this. What's not written in this part of the notes, but it's out elsewhere, is that the k here is special. K can be any real number. And we really mean it, any real number whatsoever. So when we're looking into, say, something like square root of 4 plus x, we could re-express this as 4 plus x to the power of 1/2, and that's the k value. So this tells us the binomial series is in fact going to allow us to see how to expand a square root across addition like this. The side effect, though, is you get infinitely many terms, whereas in the other problem, you got finitely many terms when the integer was, or excuse me, the k value was a nice integer like this. If you take k to be a fraction, a rational number, then you're probably dealing with infinitely many terms. But they involve factorials in the denominator, so this is really fast convergence over here. So that's what the first part of the notes is going to be about, working with the binomial series. So we'll have this collection of power series here. This will be helpful when you're looking through the homework problems. And if we need any of these results for any final exam question that's going to be asked, I'll cite these as well. I'm not expecting you to have verbatim memorization on every single one of these. Well, that's what these notes are all about. Let's check the clock. I think we have enough time to get started on this one right here. We're going to find the Maclaurin series representation for 1 plus x power k. Kind of really just a review on Taylor Maclaurin series itself. but it's also part derivation as well for the binomial series. The binomial series formula is kind of complicated to look at, but if we see how it gets built, it helps us learn how to work with it. So let's work on a Maclaurin series. Because the Maclaurin series was requested, this means the center is A set to 0. That's really usually, if we're looking into a power series, almost always that's our first discussion. What is the center? But now we're seeing why it takes such an important role. It's going to tell us how to take and put together our power series. So first thing to write down is f of x, 1 plus x to the power k. And we made no assumptions on k. It's just a real number. So we're going to operate on that assumption only. Then f at the center 0. It's not so bad. K goes to 0. So, excuse me, x would go to 0. So this is 1 to a power k, which is just a 1. K is just a variable in this problem. We don't know its value other than it's a real number. So set x to 0 on the center, and that's our first row. Next row, we're doing derivatives. F prime of x says this k value is going to come down now as a coefficient. K times 1 plus x. This now is going to be a group raised to power k minus 1. So come over here, evaluate it at the center. F prime of 0, it's 1 plus 0 to power k minus 1. This part continues to still just be a 1. Even with the power change, a 1 to any power whatsoever is automatically a 1. So the only thing that survives here is just the k. So here's our k value, and then next row. Second derivative of f at x is k times k minus 1. This is starting to look like a factorial pattern, but it's not, because recall k can be pi, for example. This would then be pi times pi minus 1, whereas the factorial function operates on integers. And factorial would mean n is like a 5 or a 12, maybe a 70, something like that. But this is like the next closest thing. It's operating like a factorial. So k times k minus 1, 1 plus x to the power k minus 2. K could have been any real number, and if it was an integer, we might be looking at factorials here legitimately. Much like the natural logarithm problem, that's where factorials were coming up. So now second derivative at 0, reminder is 1 plus x to the power k, where the x is 0 is still just a 1. All we're grabbing are the coefficients. Now k times k minus 1. Let's do maybe just a couple more terms. This pattern is not as bad as the last one. The third order derivative is k minus 1, power k minus 2 comes down, and it's 1 plus x, power k minus 3. So at the center, f triple prime at 0 is k minus 1, k minus 2. And notice I'm running out of horizontal space for my next row. These just get really too long. But sometimes the pattern is not too really hidden inside here. You might be able to say what the fourth order derivative is without even calculating it. My claim is that the fourth order derivative, right at 0, if it's going to maintain the last patterns that we see above, it should be k minus 1, k minus 2, and then new factor, k minus 3. So does that make sense to folks so far on that fourth order derivative? It's kind of a test on, do we see what the pattern is? If we can compute one term like that without the derivative on the left, then that means you should be able to do this one. The nth order derivative at 0, the center, should be, let's take a look at how this goes. So if n was an index 0, we would just have a 1. Then it would be k times k minus 1, and so on. So let's write in k minus 1, k minus 2, dot, 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 k minus, and let's see how these relate. The third derivative is what related to k minus 2. Fourth derivative relates to k minus 3. So the nth derivative should relate to, let's see here. We already had the k minus. Let me take that back. K minus n minus 1. That may be kind of hard to see. Let me see if this makes sense at the moment. Can we fit that in on this one is the test. Let's rewrite fourth order derivative at 4 at 0 to be k minus 1, k minus 2, k minus, then the n value minus 1. The n value on this one is going to be at 4. And yeah, that simplifies, right? 4 minus 1 gives us the 3. This is just a k minus 3. We were forced to write it in this way, but we could distribute the negative sign through to get k minus n plus 1, or k minus n minus 1, kind of the same thing in a way. This is just conveying you took the n minus 1 term coming from the nth order derivative if you left it in that format. So that's how all of this works so far. Any questions at the moment? Okay, so now putting this all together, we definitely want to count how many factors is that really? Well, up here, it was 4 factors. Here, it was 3 factors, then 2 factor, then 1 factor, and then just 1 itself. So what we might do is say the nth order derivative at 0 has n factors. We don't know necessarily if we need that information right now, but in a problem working with this, that could be surprisingly relevant. It depends on what k is. If k is, say, maybe a negative integer, these could potentially alternate, or maybe not alternate, but it can involve a negative power that we'd be factoring out. We'd be factoring out -1 to power n is what that would be telling us. So knowing the number of factors is going to give us more algebraic leverage on this when we do it as a problem on the next examples. Next thing we need for the Maclaurin series is Cn. Cn is going to be defined to be Fn at 0 divided by n factorial. And so now it looks like this. Let me fix the color coding just a bit. Over n factorial, we place in the numerator k times k minus 1, k minus 2, k minus n minus 1. And now we give this a name. This expression right here comes up often enough that it gets labeled in this way, k choose n. If you've taken combinatorics, this is the same kind of function that you're dealing with. Usually you write n choose k, so this is backwards. It feels weird. So this is really k choose n, but this one is allowing k to be any real number whatsoever. This is referred to as the binomial coefficient. And in this binomial coefficient, a weird kind of mathematical thing happens. By definition, we take k choose n is how we usually say the binomial coefficient. K, I don't want to say k over n because then it feels like a fraction, but you can't put a fraction bar there. That has no meaning. So k choose 0 is defined to be 1. So this is something that people just take by definition. The reason you have to do that is, if you look at this line right here, I think it makes sense when n is 1. If n is 1, you're just going to get only one term, k minus n minus 1 minus 1, then it's just a k. When n is 2, we get 2 factors. It'll be k, then this is the final factor, k minus, it's a 2, so just k minus 1. It fits here. And so does all the rest, but we kind of glommed over the fact that that one doesn't fit. this one doesn't really actually fit in this process. If n is set to 0, well, how many factors do we have? We said n factors, that would mean there's no factors? Nothing here is what this is saying. That's a pattern break, a really bad one. And so people fixed it this way. They just say, by definition, say the binomial coefficient outputs a 1. They didn't have to do that. But if you do that, it allows you to index on the binomial series at 0 because we don't have an exception right at the first term when n itself is 0. In other words, people made this definition just like an extra rule in the rule book, even though it didn't fit the format of this numerator, because they're trying to avoid that situation where we write down a binomial series, but every time we write it down, we have to write in one term that never fits the pattern. So that was the goal with saying by definition, k choose 0 evaluates to 1. It doesn't based on the information above, just something extra we baked in. Kind of like saying 0 power 0 is a 1, where some calculators say that's supposed to be undefined. But we can now put all this together and say, finally, therefore, the function we started with, 1 plus x power k, can be re-expressed as a summation from 0 to infinity of k choose 0. Let's use that color because that's a weird structure to use, especially with an exception baked right into it. Then we take x minus the center. The center here was 0, so we don't have to worry about minus 0. We just raise the result to power n. So that's the binomial series. And facts about this binomial series is that the radius of convergence on this is just a 1. We could show it by the ratio test, but you can see already, ratio test is going to be interesting on this one. It can be done, but let me know if you would like to see it done. Otherwise, I'm just going to inherit that as a consequence as part of the binomial series definition. So that's our derivation. We don't do a lot of derivations in this class, only when it makes sense and it's reinforcing tools we've already used, like the Maclaurin series is more important here. But it's good to see where this weird thing comes from, why there's an exception. And when we come back to these notes after our third exam, we'll move forward and find the representation for root 4 plus x squared, which is a good one to do because a common mistake on this is to write it's root 4 plus root x squared. Let me try again on that. That's absolutely false. You can't split a square root across addition like that. So we'll see what the right stuff is that goes inside here. So this example 2 will culminate by expanding a square root expression where we've been told constantly in algebra it's forbidden. It really still is. That's why we get infinitely many terms. There's no finite expansion here. But any last questions, folks, with these notes so far? Okay, example 2 is a really tricky kind of problem. So we're going to save this and not try to attempt it in 3 minutes and some change. Just last reminders about the upcoming third exam. Any questions you might have while you're studying, just send them out to me by email. I'll be very happy to help out. As far as my schedule goes, I'll be on my computer checking emails quite a bit on Friday. I'll be checking all emails in the morning on Saturday. I'll be working quite a bit on Sunday as well, the 20th. So sending emails any time of the day is perfectly fine on those days. Really any days, but I'll be mostly responding to whatever emails is in my list on the weekend there. Don't forget to take a look into the formula sheet as you're studying, just to make sure you're orienting yourself to where everything is to maneuver through this content. And I'll see you all on next Monday. Just a reminder, if you're on the online class, we won't have an official Zoom meeting on Monday. We'll all just be in exam mode. But have a great weekend, folks. I'll see you all next time.
Sorry.
Of the binomial,
Yeah.
this one right here.
Just the part that's the K.
Oh, K choose N. Yeah, other ways to write K choose N, which is probably more familiar, is usually it's N choose K, actually.
Yeah.
And I believe you go N factorial, K factorial, N minus K factorial is the
Yeah.
usual thing in combinatorics.
Permutations or combinations.
Yeah, exactly. You're
Yeah,
counting
but
the
then-
number of
I
weird
was
things
trying to-
happening.
Before you said that it was like issues that.
Yeah.
How to express that with the F, but then.
Oh, gotcha. Oh,
And that's, I
get
came up with
in
something
that
kind of
format.
like that. Didn't, it was accurate, it was known.
Gotcha. Yeah, this is also referred to as a binomial coefficient as well. But then this is where we get a weird difference on it because when we're using this version, we're allowing K not to be an integer. It's any real number this time. So that's why this format for combinatorics starts to fall apart a little bit. This becomes something new really on its own.
There's always a finite number of numbers in a permutation and stuff.
Yeah, exactly. Yeah, when we're running this kind of problem, we're assuming as well that K ranges between 0 up to N, or else this part wouldn't have even made any sense, right?
Yeah.
It can only be 0 factorial, and that's N choose N. The number of ways of choosing N items out of a list of N things you can select. Starting to remember that stuff. Combinatorics is one of those subjects that's pretty rusty for me. It's tough. I did combinatorics a little bit because of probability, and the teacher came out and said, we're going to talk about combinatorics. This is about counting. And he tells us counting's hard. And then starts to show us all the definitions. And we all kind of agreed. Counting, that kind of counting is insanely hard, it turns out. Definitely didn't have the head for it at the time. Yeah.
How did this one?